Okay, we don't have a whole lot to go over today, so I just put these three reactions up there. So I'll give you a few moments to record this, and then we will knock them out, and then the rest of the time will be yours for handing this paper out. We'll try to keep this short, and as you know, sometimes that just doesn't happen. The first thing that we want you to establish then, okay, first of all, are these going to react? They are, even just with this. The only exception, my eraser, I'm sure it's right out in the open.
Is it over there on the window?
There's like 4 of them over there.
Or it's on the grading sheet.
On your little tray table.
I'm oh, over here. Yep. Okay. Yeah, right in plain sight. Okay. Here's an exception. Okay. Don't know why. I'm guessing it just has something to do with the pi bonds in here, and hydrogen only having 1 electron. It needs a little jump start to react. Okay. Then the next thing that we want to look at is our parent compound here. That's all of these. Are these symmetrical or asymmetrical? That's the next thing we want to ask. And then once we pass that, then decide our reagent that it's reacting with, is that symmetrical or asymmetrical? And remember, when you are describing that with someone, you really got to be careful. Is it A space symmetrical or asymmetrical? This is probably, what, the 6th time you've heard that? Okay, so is this compound symmetrical or asymmetrical? Even though there's 3 on this side and only 2 on this side, this is still considered being symmetrical. Okay, and then these 2 are asymmetrical, because keep in mind, when that happens, if that double bond is on the end, that makes that a see, there we go again. That makes it asymmetrical. That makes that asymmetrical compound, not a space symmetrical. Okay, so then this one's pretty straightforward. We have the availability to bond here and here. So then moving forward, and I don't know if this color coding helps. I would think that it does. Our double bond breaks. All of these hydrogens are still in there. Okay. Oops. And then notice we put these in here because we have a couple of voids. So then, as you would probably presume, just like yesterday, the chlorines would attach there. Okay. So would we have to do this as well, put plus? You are correct when you say no, but why are you right? Yeah, because even you say, well, you can't distinguish which chlorine is going on which, so then you still just end up with the same compound. All right. Okay. With this one, we know it's going to react. We have asymmetrical compound, asymmetrical reagent, A space symmetrical, and then moving forward, we know that's going to react. So we could go here. And then where we had these circles, that's where these chlorine atoms would then appear. Okay. But now what I want you to envision, okay, is what happens if this one is still asymmetrical, and then we make this one also asymmetrical. That changes that just a little bit. Okay. So then what happens is, notice we can still bond here. Oh shoot, now we got the same thing. That's not what I meant to do. Darn it. I had the right idea, but I meant to do it to this one. Okay. There we go. So notice we still have bonding here and here that we can do, but our reagent is asymmetrical. So what you need to do is look at one of these two. One of the chlorine stays, one of them goes. So you pick left or right. So the left one, is that staying or leaving? Okay, so that one's leaving, so it's gone. Something still has to bond there, but keep in mind, this is going to break apart right there. So if the chlorine had attached to here, then there's only one choice, and that would be the funny looking hydrogen we've got there. Okay. But now, is there another product that forms besides this one? See, I don't know if that's from leaning back in there or you're already nodding your head yes.
Just wrong.
Okay, well, you could have said, well, I already know that yes. And maybe you did.
Can you flip them?
Okay? So when we look at this, okay, well, yes, you can flip. Well, not only can you, but you have to. What's the name of this compound? It's a pentane molecule. Yeah, 3-chloropentane, because our derivative, our halogen derivative is on the third one. But notice we had asked, we said, do you want the left chlorine to go or the right one? So we picked the left one is going to disappear because we've already accounted for the right one. So then what would you presume would happen over here then? Exactly. They flip. So then this chlorine is not here, but rather our other, oh God, that looks terrible. I can't do that. I'm trying to save time here. Sorry, it's just not working. Okay. And probably holding two markers at the same time probably doesn't help. So do we have the same compound here? No. Rather, this is not 3-chloropentane, but rather 2-chloro. And that's why, if you remember from last chapter, if this was an alkane, that you would get two products over here. Okay? That's why we wanted to get you in that habit of being able to recognize that. And then now we see we have 3-chloropentane and 2-chloropentane to where, I don't know, I think the author says this is maybe like 54%. I'm not sure what the percentages are, and then maybe this is 43%. Okay, so that notice that gets us up to about 97%, and then there's just 3% of impurities in there, something to that extent. That is why we want you to be able to recognize, okay, is this an asymmetrical compound, and is it an asymmetrical reagent or a space symmetrical reagent? Okay? Because as you can see, that really makes a difference when you're reacting that with these. Okay? Because this one is the most difficult of all of them, and here's why. Do you remember the last term that we looked at yesterday was named after a Russian chemist called Markovnikov? Okay? And what happens then is now we got the conditions just right. You're going to get two products like this one, but you also have to label them. Here, we're not labeling because they're both chlorinated hydrocarbons that occur at about the same amount. That's not what happens here. Okay? So as you would guess, that what we're going to see happening, we have availability for bonding there. and there, it's going to react because of these weak pi bonds that we have here. And then as this reaction proceeds, okay, the one that you're going to get the majority of is called a major product. And you would have to label it that way, okay? So what we mean by that is we know that we're going to get this, this, and this. And then it's not that big of a deal if you put plus in there. I think it's just good practice to do that. And then we're also going to get this molecule here as well. Okay? I did that to see if we were paying attention. Yeah. Yes, we should have 4. And that was my mistake. So what we see happening here is notice that we got 2 products up at the top. We're also going to get 2 products down here. The best way to look at this is just like saying, I don't want to remember Hund's rule as orbitals fill up. Each orbital has to fill up before they start pairing together. That's a scientific explanation. We're more familiar with something like that, okay? It's saying the same thing, that orbitals have to fill up before they can start pairing, or the bus seat rule. That's how you would commonly call that. And I think that works. So in this case, a common way of looking at this would be this hydrogen is looking for whichever carbon already has the most number of hydrogens already. Okay? So this carbon has how many hydrogens? How many hydrogens? This one's got 2. This one's got 1. So what that means is when this molecule breaks apart, okay, this hydrogen is looking for whichever carbon has the most. So in that case, it's looking for this one, okay, which means then that the availability to bond here must be the chlorine. And you could say, well, we're kind of following a similar path up here. Yes, we are. But then this is the major product that's formed. You're going to, out of this solution, you're going to get probably about 95% of this compound. Okay? Which then means, just like we did up here, you just flip-flop the 2. You're going to do the same thing in this process. So now, how are we going to do that over here? So notice we got the availability to bond here and here. Put the chlorine on the first one, then hydrogen goes on this one. So then this is known as a minor product. And this, I don't know, somewhere around, it's probably not quite 5%, but you are going to get some of this chlorobutane, where the major product you're going to get is 2-chlorobutane. It's just because of how this bonding is arranged, these weak pi bonds, and how I would be led to believe it's the electronegativity of this chlorine, which is actually really, really high. So if it's high in electronegativity, then, and this is actually low in having a positive charge, this chlorine is looking for something to bond to that is more negative than positive, and that's really what happens here.
We don't have to put the percentage, do we?
No, no.
Is the major one always major?
You could write them, usually the major product, I believe, is written first, because it's the more important one. And we'll explain why that is when we put water in for this. Okay, so that is enough for today. So looking ahead at the schedule, Okay, so we're assigning that today, and I think we still have class here on Friday. I think we come in here and you take roll, and I think we're in here for the whole hour. We're not going to take a whole lot of time away from you from your homecoming experience. So we're going to review parts of these tomorrow and assign worksheet 2. And then Thursday, that's all you're doing when coming in here. This time will then be yours because, as we said before, you're busy. We're all busy in here. So that's where we're at moving forward. So we'll catch up to you next time.